today we will be studying one type of vibration which is called torsional vibration, which is very pertinent in the machinery, and various kind of application we can find of this torsional vibration in machinery. Like if we have inertia force variation in the machine, like in the IC engines, and because of the inertia change, the shaft of the IC engine may get periodic variation in the torque, and this periodic variation in the torque may leads to torsional vibration of the crankshaft. Another application in which we can have torsional vibration is the this in which we have the impulse load, like in a punching machine. There sudden release of the energy take place when the punching operation is going on, and this leads to sudden change in the torque in the flywheel shaft of the punching machine, which leads to torsional vibration. Another kind of vibration, torsional vibration, we can have in the generators when there is a sudden fault in the power line, and again when the sudden closure of that fault take place, it can have torsional vibration. And there are other kind of machine elements like gears which transmit high power. They may leads to torsional vibration in the shafts, and some other kind of elements like when we have the turbine blades where we are injecting the steam onto the blade, that may leads to some kind of torsional vibration in the steam engine shafts. Now we will be studying these type of vibrations, and we will try to see what is the motive behind studying these kind of torsional vibration. First thing which we would like to find out what is the natural frequency of the torsional vibration, and this will be helpful to us in finding out or to at least avoid the resonance condition in the machinery, because if machine is having some excitation frequency or the forcing frequency, it should not coincide with the natural frequency of the shaft, so that the resonance can be avoided. That is the main motive toward analyzing the torsional natural frequency of the shaft. Let us consider a single degree of freedom system. This is a cantilever kind of shaft in which we have polar mass moment of inertia of the disc and torsional stiffness of the shaft. Here we are assuming the shaft is massless and is having only flexibility. If we want to see what is the torsional vibration in this particular shaft, then the motion of the disc about its own axis is called the torsional displacement. So this particular displacement will be time dependent, and the disc will be oscillating about its mean position with this displacement. So to analyze the dynamics of this particular disc, we need to obtain the free body diagram of this particular disc. Let us say this is the direction of the displacement we have given to the disc. So opposite to this will be getting a force which will be given by the shaft to the disc, and from Newton's second law we can able to obtain the equation of motion of this particular disc. So sum of the external force which is acting on this particular disc can be written as this is the external force which is acting onto the disc should be equal to the inertia moment of the disc. This is the inertia moment of the disc. So equation of motion can be written as, this is a more standard form of the equation of motion. this particular equation of motion is homogeneous since we have no forcing in the system, and the solution of this we expect to be harmonic motion because the system is going under free vibration. So, the solution can be assumed as amplitude and some harmonic term like this, and here we can substitute the solution in the equation of motion. For that we need the double derivative of the solution. So, both the quantity we will be substituting in the equation of motion. So, we will get in the simplified form. Now, since the theta cannot be 0, so for non-trivial solution the quantity within the bracket should be 0, and that will give us the natural frequency of the system, this, where kT is the natural this is the torsional stiffness of the system, and IP is the polar mass moment of inertia of the disc. Let us consider another system in which we have two discs which is connected by a single shaft. So, this is a disc 1 having polar mass moment of inertia IP1, and this is another disc having polar mass moment of inertia IP2. The stiffness of the shaft is, let us say, kT. Now, to analyze this system we need to draw the free body diagram of both the discs first, and then we will be writing the equation of motion. So, this is the equation, this is the free body diagram of the disc 1, in which the first disc is having displacement theta 1, let us say, and second disc is having displacement theta 2. Let us say this particular disc is having, this is the positive direction of the theta, and there will be torque from the shaft will be coming, which is given as this. Here because the two discs are having different displacement, so the actual twist of the shaft will be the relative displacement between the two discs into the torsional stiffness, this. And another free body diagram which is of this disc 2 can be drawn. Here let us say is having displacement theta 2 here, and will be having torque which will be opposite to the displacement direction, is given like this. Now, using these two disc free body diagram we can able to obtain the equation of motion. So, let us consider the first disc. Here itself we can able to write minus kT is the torque, external torque on the disc 1 should be equal to the inertia term of the disc 1. Here this is a IP1. For this particular disc we can able to write on the similar lines the equation of motion. This, and these two equations can be written on a standard form like this. And for second disc now these two equations are the equation of motion of the two discs. The solution for that we can able to assume as a harmonic motion is taking place, because we are looking into the free vibration of these two disks. So, this is the solution for the free vibration for both the disk, as we did for the single degree of freedom system also. These two solutions can be substituted in these two equation of motion, and that will give us solution in this form. I have put these two equations in a matrix form, and the entries in the matrix will be something these are the natural frequencies. Now, for non-trivial solution of this particular equations, because these theta 1 and theta 2 cannot be 0. So, the determinant of this particular matrix should be 0, and that will give us a frequency equation. The frequency equation will be a quadratic in omega n square, and it is having this form. So, here we can able to see that the two solutions will be like this, because omega n can be taken common. So, that can be equated to first equal to 0, and then second So, these are the two natural frequency of the system. We can able to see that the first natural frequency is having 0 value, and we will try to see the physical meaning of these two natural frequency. So, for that maybe we have to go for the finding the mode shapes of corresponding to these natural frequencies. So, let us go for the calculation of the mode shape. For that we have to go back to the previous equation, this particular equation, in which we will be substituting omega n in this terms, and then we will be solving for theta 1 and theta 2. So, let us take the first equation. So, when we substitute omega n is equal to 0, we will get kt theta 1 minus kt theta 2 is equal to 0. You can see that we got theta 1 is equal to theta 2 for this, and if we want to draw the mode shape of this, this is corresponding to theta 1, this is corresponding to theta 2, they are equal. So, this is the mode shape for the first natural frequency. You can, this is corresponding to the rigid body mode, in which we do not have any twist of the shaft. Both the discs are having same displacement. So, there is no twist of the shaft and is having no practical value, because no stresses are generating into the shaft. Let us see the second mode shape that is having some practical value. So, we again will be writing the same equation, and here instead of omega n square we are substituting the actual value of the natural frequency. Here if we solve this equation, let us solve at least one more step on this. You can see that this term get cancelled. So, this equation is getting simplified. So kt ip2 minus ip1 kt minus ip2 kt theta 1 minus kt theta 2 is equal to 0. So here this particular term is again getting cancelled. So finally we will get theta 1 by theta 2 is equal to minus of ip2 by ip1. This is the relative displacement of the two disks corresponding to the second mode, which is, you can see, is inversely proportional to the mass moment of inertia. That means if disk is having large mass moment of inertia, it will be having less displacement, and this negative sign represent that two disks will be having different phase. So let us draw the mode shape for this. So if we are considering theta 1 as positive, so theta 2 will be negative, and their amplitude will be inversely proportional to the mass moment of inertia, polar mass moment of inertia of the disk. In the second natural frequency, we have seen that the mode shapes, there is a point. If we go back to the previous slide, here there is no displacement of the shaft. That means we can able to consider that left half portion of the shaft from this point is a cantilever kind of shaft, and similarly in the right hand side also we can able to consider that shaft as a cantilever. So we can consider this as like this, in which this end is fixed completely. Similarly we can able to draw another cantilever with in the right hand side, and for this polar mass moment of inertia is, let us ip1, length of this is, let us say, L1. So it will be interesting to find out the location of this particular position where displacement is 0. This is called a node where there is no angular displacement is taking place. So we have seen from the previous mode shape that this particular two rotor system can be considered as two single degree of freedom systems, and the natural frequency of that particular system can be written like this, which will be equal to the natural frequency of the second single degree of freedom system for the cantilever case. And this particular equation, because we know the natural frequency of the system, it will remain same for both the cases, and ip1 and ip2 we know. So from here we can able to get the kt1, which will be this, and for torsional vibration we know that this is given by L1, and this particular equation will give us the position of the node. Okay. On the same line we can able to obtain the position of the node from this also, but that will, this is a redundant equation. Now we will consider another kind of system in which two disks are there, but shaft is having a different dimensions in between. So that particular type of shaft is called stepped shaft, because in some application we may find these kind of shafts. So let us first see the system. This is the axis of the shaft. This is one segment of the shaft. Then there is a step like this, then another step is there, and then there is a disk here. So disk ip1, ip2, and corresponding displacements are theta 1 and theta 2. In this particular case, let us say the lengths of these are given is this, and they have different diameters also. So this particular system is exactly similar to the previous case, only difference is here we have different shaft diameters of the shaft. So it will be very good if we can convert this particular system to equivalent uniform shaft system, and that means if this particular system we can able to convert to a system like this. Let us say this equivalent shaft diameter is L3 and this is the equivalent length of the shaft. So if we can convert this system to this, then the analysis which we performed in the previous section is valid. So let us see how we can able to do it. To convert the step shaft into the uniform shaft, the main aim is, because the shaft is giving the only the stiffness into the torsional vibration. So if we can have some kind of equivalent stiffness, then we can able to obtain the equivalent system. So because these step shafts are connected by series, so we can able to write the equivalent stiffness of the uniform shaft like this, because we have 3 stepped shaft. So these are the torsional stiffness of the 3 stepped shaft, and this is the equivalent stiffness of the overall system. This can be, because we know K is given by Gj by L, where this is the modulus of rigidity, J is the polar moment of area, L is the length of the shaft segment. So using this equation can be converted into or because G is common, so I have eliminated from both the sides. Which can be written as like this. Once we obtain the equivalent length of the uniform shaft, then the analysis in the previous section is valid here. We can obtain the mode shape of the system, we can obtain the natural frequency of the system. Now the question comes, because those mode shapes are corresponding to the equivalent system, how we can able to convert that into the real system, we would like to see now. So let us draw the actual system first. This is the actual system. We converted this into equivalent system like this, because we took smaller diameter for the equivalence, so we will be getting lesser length of the shaft. The mode shape for this particular system is, let us say, this one, where this is the nodal position. Now if we want to find out the various positions of the shaft onto the equivalent system, if this is the L3 in equivalent system, that will remain L3, and corresponding to this second segment, let us say this is L2, and this is L equivalent to, and the third one is that is corresponding to L1 equivalent L1, and in actual system is L1. Now let us say the position of the node, this is the node position on the equivalent system is A from the this position LE1 position. So in the equivalent system we can able to locate the node position as we did in the previous case. Where KT1 is the stiffness of the first part of the system, this one up to this, and from here we can able to obtain A because other quantities are known. Now we need to find out the equivalence of this in the actual system. Where is the node in the actual system? To find out the position of the node in the actual system, let us see the previous relations which we had for the equivalent system for the segment 2, this. So if A is the equivalent the node position for in the segment 2, then let us say A prime is in the actual system. Similarly, if we have from other side, that is from the right side of the element 2, the node position is given by B in equivalent system and B prime is in the actual system, then we can have this relation. And if we take the ratio of these two equations, we will get A by B is equal to A prime by B prime. So you can see that once we have located the node in the actual in the equivalent system, in the actual system also the node positions will be there in this in the same proportion, where this A prime and B prime are like if node is here, so A prime will be this and B prime will be this. Now we will consider the 3 rotor system, and in this particular 3 rotor system the basic principle of the 2 rotor system is equally valid here. Here 3 rotors are connected by 2 shafts, so we can have, if we want to see the motion, especially the how they will be vibrating in free or normal modes, either they can have one node in between the shaft or they can have 2 nodes in the shaft. If they have one node in the shaft, then obviously the 2 extreme discs will be having opposite phase. This will be seen in more detail. And if there are 2 nodes in between the shaft, then the 2 discs at the extremes will be having same phase. So let us see this particular analysis. So this is a one rotor connected by a shaft. This is another rotor. For simplicity we are considering the uniform shaft, but we can able to take non-uniform shafts also, but then we have to go for the equivalent system in that case. So let us say their mass moment of inertia are like this, and this is, these are the torsional stiffness of the shaft. Lengths of the shafts are, let us say. Now if we directly want to go for the mode shape analysis first, and then from there we will try to find out the natural frequency of the system. Let us say there is only one node in this particular system, then how the mode shape look like. So let us say node is here. So this is the mode shape which will be. So here we have theta 1, theta 2, theta 3. Theta 3 is negative. As I said earlier, when there is one node, then theta 1 and theta 3 will be having opposite phase. In another case, when we have two nodes, one node is here, another node is here. Let us say the position of those nodes are LA from left hand side and LC from right hand side. On the same lines, we can able to write this as LC is the position of the node from the right hand side. This regarding the mode shapes. We have seen that either it can have one node in between the shaft or it can have two nodes in between the shaft. So let us consider the general case when it is having two nodes in the shaft. So how we can able to analyze? Left part of the shaft will be a cantilever because there is no displacement at this point. So we can consider this as a cantilever beam. Another is the extreme right position. There also we can able to consider that as a cantilever beam, and in between this, the middle portion will be having a fixed beam, fixed rod, and the disc is in between those fixed ends. So there are three systems now, but because they are vibrating in natural mode, all the natural frequency of these systems will be same. So let us write those equations of motions now one by one. Disk at extreme left, we can able to write the frequency equation as and if we substitute for the torsional stiffness, because L is the length of that left hand side cantilever beam. On the same line, we can write for the third disc. This is the natural frequency for the third disc. And for the middle rotor, will be having natural frequency this T2 is given as now these three frequencies 1, 2 and 3 for 3 discs, because they are belonging to the same system, their natural frequency should be same. So we can able to equate these three equations, and our aim would be to obtain either LA or LB. Eventually these equations, when you equate these three equations, will get a quadratic equation either in terms of LA or LB. So let us see the steps. So if we equate the natural frequency of the first disc and this third disc, we will get this equation, and if we equate the natural frequency of the first and the second disc, we will get equation which can be written as in this particular equation. Now this particular equation contain both LA and LC. So from this equation we can able to eliminate LA from this particular equation. So if we do it, will what we have to do, we have to substitute, let us say LA is equal to LC IP3 by IP1, and if you substitute this here, here and here, and if you solve it, you will get this following equation. LC square minus is a big equation LC and then plus IPB L1 L2 is equal to this is 2. Okay. So this is a quadratic equation in LC. We expect 2 solutions from this, and those will be corresponding to the one corresponding to the 2 node system and another corresponding to the single node system. And let us go back to the mode shapes. So we'll be from that quadratic equation we'll be getting 2 solutions for LC. So if you see in this mode shape, one will be corresponding to this and another will be corresponding to this, and because we have a relationship between the LA and LC, so we will be getting 2 values of the LA also. So one value will be this one, another value will be if we extend this particular line up to here, so LA will be, second value of LA will be corresponding to this, having no meaning, but because our solution gives 2 value of LA, so that is the interpretation of those 2 solutions. Now let us consider some examples so that our concepts are more clear. First we will consider the 2 degree of freedom system. So first shaft is having 0.06 kg meter square mass moment of inertia, second shaft is having 0.02 kg meter square, and diameter of the shaft is, let us say, 0.1 meter, length of the shaft is 0.6 meter. We need to obtain the natural frequency of this system. Let us say the modulus of rigidity is given as 0.8 10⁻11 Newton per meter square. Now with this information we can able to calculate the polar moment of area of the shaft, that will be this. So we know the diameter, so it comes out to be this much. Now because the torsional stiffness is given by G, this expression, so we can able to substitute these quantity here. Length of the shaft is 0.6, so this gives us the stiffness of the shaft as Newton meter per radian. Now we will be substituting these values in the natural frequency equation. First natural frequency remains 0, rigid body mode. Second natural frequency we obtained is IP1 plus IP2 kT divided by IP1 IP2. So if we substitute these values here, 0.06 plus 0.02 into 1.31 10 raised to minus 10 raised to 6 divided by 0.06 into 0.02. So this gives us 9345.3 radians per second as the second natural frequency. You can see this natural frequency is quite high, in the range of 9000 radians per second, as compared to the transverse vibration. Generally these natural frequencies are very high. Now let us see the mode shapes. Corresponding to the first natural frequency, will be having both the displacement same. So mode shapes remains like this, both are same, theta 1 and theta 2. Corresponding to the second natural frequency, we will be having mode shape which is 0.06 by 0.02 minus, so it comes out to be minus 3. So the mode shape will be something, if we have 1 here, second will be having minus 3 displacement. So this is corresponding to the second natural frequency mode shapes. Now we will be considering another kind of system in which gears are there, and in such systems also we face problem of torsional vibration, and here our aim would be to obtain the natural frequency of the system, so that we can avoid any resonance condition from this. So generally in this particular kind of systems, because of the gear, we will be having different speeds of the shafts, maybe because there will be a gear ratio after the gears. So there will be either steep speed reduction or speed increase in the shaft will take place. So let us see how we can able to analyze for torsional vibration case such systems. Here our main aim would be, if we can able to convert these kind of systems to the some kind of equivalent single shaft system, then we can able to analyze using the analysis which we already covered previously. So let us see the geared system. So let us say we have one shaft which is connected by a gear, and then with another gear we are transmitting torque to the another shaft. Let us say the mass moment of inertia of this particular rotor is IP2, and here there is another rotor or disc which is having mass moment of inertia IP1. here we are assuming that there is mass moment of inertia, the polar mass moment of inertia of gears are negligible, but later on we can able to add that also. For simplicity in this particular analysis, we are not including the polar mass moment of inertia of the gears. So, this is the gear system in which we have speed of this omega 1. The twist of the gear 1, torsional displacement of the gear 1 is theta 1, and the torque which is coming onto the shaft at gear 1 is, let us say, T. Now, because of this gear pair, there will be a change in the angular velocity of the shaft 2, let us say that is omega 2, and there is change in the torque, that is Nt, N is the gear ratio, and there will be change in the angular twist of the shaft, that is, let us say G2, that G2, theta G2 is related with theta G1 by the gear ratio. Actually, this is theta G1, let us say, to distinguish between this rotor and the gear displacements. Now, we want to analyze this particular gear system. So, if we consider this particular system is enclosed in a black box like this is a black box, and we want to find out an equivalent system in which, let us say, this is the IP1, this is the shaft, and after this, corresponding to this particular box, let us say we are having equivalent stiffness Ke and equivalent polar mass moment of inertia, this one. So, if we can convert the geared system into this particular system, what we will find that we already analyzed this 2 disk system. So, our analysis will be valid whatever we have covered previously for geared system also, if we can find out the equivalence of that. So, our aim would be to obtain first to obtain the equivalent system of the geared system, and the here, because for finding the equivalence we will be having 2 quantities which will be of our concern. One is the strain energy in the system. So, whatever in the strain energy is there in the original system should be equal to the strain energy in the equivalent system. Similarly, another quantity, that is the kinetic energy of the actual system and of the equivalent system, should be same, and based on these 2 energy we will be obtaining what should be the equivalent stiffness of the equivalent system and what should be the polar mass moment of inertia of the equivalent system. So, let us first see the equivalence of the strain energy. So, to equate the strain energy in the system of the actual system and the equivalent system, what we will be doing, first we will be fixing, let us say, this particular disk will fix it and will give to gear 1 theta G1 rotation. So, what we are doing, we are fixing the IP to the disk 2 by some means, and we are giving gear 1 theta G1 displacement, and we will try to find out how much strain energy is stored in the gear this shaft 2, and that will be given by this is the strain energy in shaft 2, that will be half stiffness of the shaft, and the angular twist of that is theta G 2, and we have relationship between the theta g1 and theta g2 like this. This is the square of that, here also square. Minus sign will be having no meaning here because this is square of the quantity. So here will be this is the strain energy stored in the actual system. Now the strain energy in the equivalent system can be written as, this is the torsional stiffness of the equivalent system and is getting twist same as of the gear 1, this. So now these two energy, if we equate, we can see that we get this relationship. That means if we divide the torsional stiffness of the actual system of the shaft 2 by the gear ratio square, we will get the stiffness of the equivalent shaft system. To find out the equivalent polar mass moment of inertia of the equivalent system, now we have to equate the kinetic energy of the actual system and the equivalent system. So first let us see kinetic energy as omega 2 prime square, where omega 2 prime is nothing but actual speed of the rotor plus its angular twist. And kinetic energy of the equivalent system can be written as omega 1 let us say equivalent square. So here omega equivalent is omega 1 plus theta g1 dot. This is the angular displacement of the gear 1. Now because we have a relationship between the gear displacement 1 and gear displacement 2, so we can substitute this equations in the kinetic energy and we can equate them. So let us start equating them. So this is the kinetic energy of the actual system, in which we replaced omega 2 by omega 1 by n plus theta g2 has been replaced by this quantity is nothing but theta and time derivative with respect to time, and whole square should be equal to kinetic energy of the equivalent system Now if we simplify this, we can able to see that the equivalent mass moment of inertia, polar mass moment of inertia, comes out to be IP2 by n square. So here also we can able to see that the polar mass moment of inertia of the equivalent system can be obtained if we divide the polar mass moment of inertia of the actual system divided by the square of gear ratio. Okay. Now once we obtain the equivalent system, which is something like this, in which we have one disk here, another disk here, and gear is somewhere here. So if we want to obtain, because this system we already analyzed previously, so the mode shape can be obtained from this. This is the mode shape. Now this particular mode shape is for the equivalent system. Now how we will be obtaining the mode shape for the equivalent actual system to be seen, because this is the location of the gear. Okay, this is the node position where is no displacement is taking place. So for this particular case, the node is coming before the gear here. Okay, so let us see what is the correction we need to make on the this mode shape to get the actual mode shape. So what we need to do, up to this point there is no change, because there is no change in the speed of the shaft up to that point, because gear is here. After this, because whatever the displacement is taking place, because these are nothing but theta 1 and theta 2, so whatever the displacement is taking place in this range has to be divided by n, that gear ratio. So the mode shape will change like this. So you can see that there is a step change of the mode shape at the gear ratio will take place, and this is the modification we need to incorporate, because we have converted the actual system to equivalent system and we analyze the system. Now to get the mode shape in the actual system, this particular modification has to be considered. So this is one important aspect we need to consider in this particular case. In this particular lecture, we have seen the introduction to the torsional vibration. We considered single degree of freedom system, 2 degree of freedom system, 3 degree of freedom system, and then we have seen the how we can analyze the geared system in which the two shafts are having different speeds. Now in future, in the next lecture, we will be considering more general methods available for analyzing the multi degree of freedom systems.